The Black Hole War by Leonard Susskind, continued. Disc 2. The last symbol in this equation, g, is a numerical constant called Newton's constant. Newton's constant is not something that can be deduced from pure mathematics. To find its value, the gravitational force between two known masses at some known distance must be measured. Once you've done that, you can calculate the force between any two masses at any distance. Ironically, Newton never knew the value of his own constant. Because gravity is so feeble, g was too small to measure until the end of the 18th century. At that time, an English physicist named Henry Cavendish devised a clever way to measure extremely small forces. Cavendish found that the force between a pair of 1 kilogram masses, separated by 1 meter, is approximately 6.7 times 10 to the negative 11th power newtons. The newton is the unit of force in the metric system. It's equal to about 1/5 of a pound. Thus, the value of Newton's constant in metric units is g equals 6.7 times 10 to the negative 11th power. Newton had one lucky break in working out the consequences of his theory, the special mathematical properties of the inverse square law. When you weigh yourself, some of the gravitational force pulling you toward the Earth is due to mass just beneath your feet, some is due to mass deep within the Earth, and some comes from the antipodal point 8,000 miles away. But by a miracle of mathematics, you can pretend that the entire mass is concentrated at a single point, right at the geometric center of the planet. The gravity of a ball of mass is exactly the same as if all the mass were concentrated at a point in the center. This convenient fact allowed Newton to calculate the escape velocity from a large object by replacing the large mass with a tiny mass point. Here is the result. Escape velocity equals the square root of 2 mg divided by r. The formula clearly shows that the bigger the mass and the smaller the radius, r, the larger the escape velocity. It's now an easy exercise to compute the Schwarzschild radius, r sub s. All you have to do is plug in the speed of light for the escape velocity and then solve the equation for the radius. R sub s equals 2 mg over c squared. Note the important fact that the Schwarzschild radius is proportional to the mass. That's all there is to dark stars, at least at the level that Laplace and Michel were able to understand them. Chapter 3. Not Your Grandfather's Geometry. In the old days, before mathematicians such as Gauss, Bolyai, Lobachevsky, and Riemann messed around with it, geometry meant Euclidean geometry, the same geometry that we all learned in high school. First came plane geometry, the geometry of a perfectly flat, two-dimensional surface. The basic concepts were points, straight lines, and angles. We learned that 3 points define a triangle, unless they are on a common line. Parallel lines never intersect, and the sum of the angles of any triangle is 180 degrees. Later, if you had the same course that I did, you stretched your powers of visualization to 3 dimensions. Some things remained the same as in 2 dimensions, but other things had to change, or there wouldn't be any difference between 2 and 3 dimensions. For example, there are straight lines in 3 dimensions that never meet, but that are not parallel. They are called skew lines. Whether it is 2 dimensions or 3 dimensions, the rules of geometry remain the ones that Euclid laid down sometime around 300 BC. However, other kinds of geometry, geometries with different axioms, are possible even in 2 dimensions. The word geometry literally means measurement of the Earth. It's ironic that had Euclid actually taken the trouble to measure triangles on the Earth's surface, he would have discovered that Euclidean geometry doesn't work. The reason is that the Earth's surface is a sphere. I am, of course, referring to an idealized, perfectly round Earth, not a plane. Spherical geometry certainly has points and angles, but it's not so obvious that it has anything that we should call straight lines. Let's see if we can make any sense out of the words straight line on a sphere. A familiar way to describe a straight line in Euclidean geometry is that it is the shortest route between 2 points. If I wanted to construct a straight line on a football field, I would put 2 stakes in the ground, and then stretch a string between them as tightly as possible. Pulling the string taut would ensure that the line was as short as possible. That concept of the shortest route between 2 points can easily be extended to a sphere. Suppose our goal is to find the shortest possible air route between Moscow and Rio de Janeiro. We need a globe, 2 thumbtacks, and some string. Placing the tacks at Moscow and Rio, we can stretch the string across the globe's surface and determine the shortest route. These shortest routes are called great circles, such as the equator and the meridians. Does it make sense to call them the straight lines of spherical geometry? It doesn't really matter what we call them. The important thing is the logical relationship between points, angles, and lines. Being the shortest route between 2 points, such lines are in some sense the straightest possible on a sphere. The correct mathematical name for such routes is geodesics. Whereas geodesics in a flat plane are ordinary straight lines, geodesics on a sphere are great circles. Having these spherical replacements for straight lines, we can go about constructing triangles. Pick 3 points on the sphere, say Moscow, Rio, and Sydney. Next, draw the 3 geodesics connecting the points pairwise, the Moscow-Rio geodesic, the Rio-Sydney geodesic, and finally the Sydney-Moscow geodesic. The result is a spherical triangle. In plane geometry, if we add the angles of any triangle, we get exactly 180 degrees. But looking carefully at the spherical triangle, we can see that the sides bow out and make the angles somewhat larger than they would be on a plane. The result is that the sum of the angles of a spherical triangle is always larger than 180 degrees. A surface whose triangles have this property is said to be positively curved. Can there be surfaces with the opposite property, namely that the sum of the angles of a triangle is less than 180 degrees? An example of this kind of surface is a saddle. Saddle-shaped surfaces are negatively curved. Instead of bowing out, the geodesics forming a triangle on a negatively curved surface are pinched in. Thus, whether our limited brains can envision curved three-dimensional space or not, we know how to experimentally test for curvature. Triangles are the key. Pick any 3 points in space and stretch strings as tightly as possible to form a 3-dimensional triangle. If the angles add up to 180 degrees for every such triangle, the space is flat. If not, it's curved. Geometries far more complicated than spheres or saddles can exist. Geometries with irregular hills and valleys having regions with both positive and negative curvature. But the rule for constructing geodesics is always simple. Imagine yourself crawling on such a surface and following your nose forward, never turning your head. Don't look around, don't worry about where you came from or where you are going, just myopically crawl straight ahead. Your path will be a geodesic. Imagine a man in a mechanized wheelchair attempting to navigate a desert of sand dunes. With only limited water, he must get out of the desert quickly. The rounded hills, saddle-shaped passes, and deep valleys define a land of positive and negative curvature, and it's not entirely obvious how best to steer the chair. The driver reasons that the high hills and deep valleys will slow him down, so at first he steers around them. The steering mechanism is simple. If he slows one of the wheels relative to the other, the chair will turn in that direction. But after a few hours, the driver begins to suspect that he is passing the same shapes that he passed earlier. Steering the chair has led him in a dangerous, random walk. He now realizes that the best strategy is to go absolutely straight ahead, turning neither to the left nor to the right. Just follow your nose, he says to himself. But how to make sure that he is not wavering? The answer soon becomes obvious. The wheelchair has a mechanism that locks the 2 wheels together so that they turn like a rigid dumbbell. Locking the wheels in this manner, the man takes off, making a beeline for the edge of the desert. At every point along the trajectory, the traveler seems to be going in a straight line, but looked at as a whole, his path is a complicated, winding curve. Nevertheless, it is as straight and short as possible. It wasn't until the 19th century that mathematicians began to study new kinds of geometry with alternative axioms. A few, such as Georg Friedrich Bernhard Riemann, entertained the idea that real geometry, the geometry of real space, might not be exactly Euclidean. But Einstein was the first to take the idea seriously. In the general theory of relativity, the geometry of space, or more correctly, space-time, became a question for experimenters, not philosophers or even mathematicians. Mathematicians can tell you what kinds of geometries are possible, but only measurement can determine the true geometry of space. In crafting the general theory of relativity, Einstein built on the mathematical work of Riemann, who had envisioned geometries beyond spheres and saddle surfaces, spaces with lumps and bumps, some places being positively curved, others negatively curved, geodesics winding over and between these features in curving irregular paths. Riemann thought only of three-dimensional space, but Einstein and his contemporary Hermann Minkowski introduced something new: time as the fourth dimension. Try to visualize that. If you can, you have a very unusual brain. The special theory of relativity. Even before Einstein began to think about curved space, Minkowski had the idea that time and space should be combined to form four-dimensional space-time, declaring rather elegantly, if somewhat pompously, henceforth space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality. Minkowski was the first to realize that a new four-dimensional geometry was the proper framework for Einstein's special theory of relativity. The quote is from Space and Time, an address delivered at the 80th Assembly of German Natural Scientists and Physicians on September 21, 1908. Minkowski's flat or uncurved version of space-time became known as Minkowski space. In a 1908 lecture to the 80th Assembly of German Natural Scientists and Physicians, Minkowski represented time as the vertical axis, making do with a single horizontal axis to represent all three dimensions of space. The audience had to use a bit of imagination. Minkowski called the points of space-time events. The common usage of the word event implies not only a time and a place, but also something happening there. For example, an event of momentous importance took place at 5 hours 29 minutes 45 seconds a.m., July 16, 1945, at Trinity, New Mexico, when the first atomic weapon was tested. Minkowski intended a little less by his use of the word event. He meant only a specified time and place, regardless of whether anything actually happened there. What he really meant was a place and time where an event might or might not happen, but that was a bit of a mouthful, so he just called it an event. Lines, or curves through space-time, play a special role in Minkowski's work. A dot in space represents the position of a particle. But to draw the motion of a particle through space-time, one draws a line or curve sweeping out a trajectory called a world line. Some sort of movement is inevitable. Even if the particle stands perfectly still, it nevertheless travels through time. The trajectory of such a stationary particle would be a vertical straight line. The trajectory of a particle moving to the right would be a world line tilting to the right. Similarly, tilting the world line to the left would describe a particle moving to the left. The greater the tilt away from the vertical, the faster the particle is moving. Minkowski represented the motion of light rays, the fastest of all objects, as lines drawn at a 45-degree tilt. Since no particle can move faster than light, the trajectory of a real object cannot tilt more than 45 degrees from the vertical. Minkowski called the world line of a particle moving slower than light time-like, because it is close to the vertical. He called the trajectories of light rays inclined at 45 degrees light-like. Proper time. Distance is a fairly easy concept for the human brain to grasp. It's especially easy when distance is being measured along a straight line. To measure it, you need only an ordinary ruler. Measuring distance along a curve is a little harder, but not much. Just replace the ruler with a flexible tape measure. Distances in space-time, however, are more subtle, and it's not immediately clear how to measure them. In fact, no such concept existed until Minkowski invented it. Minkowski was particularly interested in defining a concept of distance along a world line. For example, take the world line of a particle at rest. Since the trajectory covers no spatial distance, a ruler or tape measure must not be the right tool to measure it. But as Minkowski realized, even a perfectly stationary object moves through time. The right way to measure its world line is not with a ruler, but with a clock. He called the new measure of world line distance proper time. Imagine that every object carries a small clock with it wherever it goes, just as a person might carry a pocket watch. The proper time between two events along a world line is the amount of elapsed time between the two events, as measured by the clock that moved along that world line. The ticks of the clock are analogous to the inch marks along a tape measure, but instead of measuring ordinary distance, they measure Minkowski's proper time. Here's a concrete example. Mr. Tortoise and Mr. Hare decide to have a race across Central Park. Officials are stationed at each end with carefully synchronized watches so that they can time the winner. The racers start at exactly 12 o'clock p.m., and halfway across the park, Hare is so far ahead that he decides to take a nap before continuing. But he oversleeps and wakes up just in time to see Tortoise approaching the finish line. Desperate not to lose the race, Hare takes off like a flash and just manages to catch Tortoise as they simultaneously cross the line. Tortoise pulls out his highly reliable pocket watch and proudly shows the waiting crowd that the proper time along the segment of his world line from start to finish is 2 hours and 56 minutes. But why the new term proper time? Why didn't Tortoise just say that his time from start to finish was 2 hours and 56 minutes? Isn't time just time? Newton certainly thought so. He believed that God's master clock defined a universal flow of time and that all clocks could be synchronized to it. Picture Newton's universal time by imagining that space is filled with small clocks that have all been synchronized. The clocks are all good, honest clocks that run at exactly the same rate, so that once they are synchronized, they stay synchronized. Wherever Tortoise or Hare happens to be, he can check the time by looking at the clock in his immediate neighborhood, or he can look at his own pocket watch. For Newton, it was axiomatic that no matter where you went, at any speed, along a straight line or a curved trajectory, your pocket watch, assuming that it was also a good honest clock, would agree with the local clock in your neighborhood. Newtonian time has an absolute reality. There is nothing relative about it. But in 1905, Einstein made a hash of Newton's absolute time. According to the special theory of relativity, the rates at which clocks tick depend on how they move, even if they are perfect replicas of one another. In ordinary situations, the effect is imperceptible, but when clocks move with velocities near the speed of light, it becomes very noticeable. According to Einstein, every clock moving along its own world line ticks at its own rate. Thus, Minkowski was led to define the new concept of proper time. Just to illustrate the point, when Hare pulls out his watch, also a good, honest clock, the proper time of his world line shows 1 hour and 36 minutes. This is an extreme exaggeration, which would have required Hare to move close to the speed of light. Although they began and ended at the same space-time points, the world lines of Tortoise and Hare have quite different proper times. Before discussing proper time any further, it's instructive to think a little more about ordinary distance measured along a curve by a tape measure. Take any 2 points in space and draw a curve between them. How far apart along the curve are the points? The answer obviously depends on the curve. Imagine 2 curves connecting the same 2 points, A and B, with quite different lengths. Along the upper curve, which has a light parabola, the distance between A and B is 5 inches. Along the lower curve, with a more pronounced bend, it is 8 inches. There is, of course, absolutely nothing surprising in the fact that different curves between A and B have different lengths. Now come back to the problem of measuring world lines in space-time. Imagine a picture of a typical world line. Notice that the world line curves. That means that the velocity along the trajectory is not uniform. In this example, a rapidly moving particle slows down. The dots indicate the ticks of the clock. Each interval represents 1 second. Notice that seconds appear to tick more slowly when the angle is closer to the horizontal. That's not a mistake. It represents Einstein's famous discovery of time dilation. Rapidly moving clocks run slowly compared to slow clocks or clocks at rest. Let's consider two curved world lines connecting two events. Einstein, ever the thought experimenter, imagined two twins, I'll call them Alice and Bob, born at the same instant. The event of their birth is labeled A. At the moment of birth, the twins become separated. Bob remains at home, and Alice is whisked away at a tremendous velocity. After a period, Einstein has Alice turn around and head back home. Eventually, Bob and Alice meet again at B. At birth, Einstein gave the twins identical pocket watches, which were perfectly synchronized. When Bob and Alice finally meet at B, they compare their watches and discover something that would have surprised Newton. First of all, Bob has a long gray beard, but Alice is the image of youth. According to their pocket watches, the proper time along Alice's world line is a good deal less than that along Bob's, just as the ordinary distance between 2 points depends on the curve that connects them. The proper time between two events depends on the world line that connects them. Did Alice notice that her clock ran slow during her journey? Not at all. Her watch was not the only thing that ran slow. So did her heartbeat, her brain function, and her entire metabolism. During the trip, Alice had nothing to compare her clock to, but when she finally met Bob for the second time, she discovered that she was noticeably younger than he was. This twin paradox has puzzled physics students for more than 100 years. There is one curiosity that you may have discovered by yourself. Bob travels through space-time on a straight line, while Alice travels on a curved trajectory. Yet the proper time along Alice's trajectory is smaller than the proper time along Bob's. That's an example of a counterintuitive fact about the geometry of Minkowski space. A straight world line has the longest proper time between two events. Put that in your rewiring kit. The general theory of relativity. Like Riemann, Einstein believed that geometry, not just space but space-time, was curved and variable. He was referring not just to space but to the geometry of space-time. Following Minkowski, Einstein let one axis stand for time and the other for all 3 dimensions of space, but instead of picturing space-time as a flat plane, he imagined it as a warped surface bent with bulges and bumps. Particles still moved along world lines and clocks ticked off proper time, but the geometry of space-time was much more irregular. Einstein's laws. Surprisingly, in many ways the laws of physics are simpler in curved space-time than they are in Newtonian physics. Take, for example, the motion of particles. Newton's laws begin with the principle of inertia. In the absence of forces, every object will remain in a state of uniform motion. This simple-sounding rule, with its phrase uniform motion, hides 2 separate ideas. First, uniform motion means motion along a straight line in space. But Newton meant something stronger. Uniform motion also implies constant, unchanging velocity, that is, no acceleration. The term acceleration refers to any change in velocity, including the slowing down that we ordinarily call deceleration. To a physicist, deceleration is merely negative acceleration. But what about gravitational forces? Newton added a second law, a law of non-uniform motion, that says force equals mass times acceleration, or, to put it differently, the acceleration of an object is the force exerted on that object divided by its mass. A third rule applies when the force is due to gravity. The gravitational force on any object is proportional to its mass. Minkowski simplified Newton's notion of uniform motion with a clever insight that summarized both conditions. In the absence of forces, every object moves through space-time along a straight world line. Straightness of a world line implies not only straightness in space, but also constant velocity. Minkowski's straight world line hypothesis was a beautiful synthesis of the 2 aspects of uniform motion, but it applied only in the complete absence of forces. Einstein took Minkowski's idea to another level when he applied it to curved space-time. Einstein's new law of motion was stunningly simple. At every point along its world line, a particle does the simplest possible thing. It goes straight ahead in space-time. If space-time is flat, Einstein's law is the same as Minkowski's. But if space-time is curved, in regions where massive bodies deform and warp space-time, the new law instructs particles to move along space-time geodesics. As Minkowski had explained, a curved world line indicates that a force is acting on an object. According to Einstein's new law, particles in curved space-time move as straight as they can, but geodesics inevitably curve and bend to match the local space-time terrain. Einstein's mathematical equations demonstrate that a geodesic in curved space-time behaves exactly like the curved world line of a particle moving through a gravitational field. Gravitational force is thus nothing but the curving of geodesics in curved space-time. In one almost laughably simple law, Einstein combined Newton's laws of motion with Minkowski's world line hypothesis and explained how gravity acts on all objects. What Newton had taken as an unexplained fact of nature, gravitational forces, Einstein explained as the effect of non-Euclidean space-time geometry. The principle that particles move along geodesics provided a powerful new way to think about gravity, but it said nothing about the cause of curvature. To complete his theory, Einstein had to explain what controls the warped bulges and other irregularities of space-time. In the old Newtonian theory, the source of the gravitational field was mass. The presence of a mass, such as the sun, creates a gravitational field around it, which in turn influences the motion of the planets. It was therefore natural for Einstein to conjecture that the presence of mass, or equivalently of energy, causes space-time to become warped or curved. John Wheeler, one of the great pioneers and teachers of modern relativity theory, summed it up in one concise slogan: space tells bodies how to move, and bodies tell space how to curve. He meant space-time. Einstein's new idea means that space-time is not passive. It has properties such as curvature, which respond to the presence of masses. It is almost as though space-time is an elastic material, or even a fluid that can be affected by the objects moving through it. The connection between massive objects, gravity, curvature, and the motion of particles is sometimes described by an analogy that I have mixed feelings about. The idea is to think of space as a horizontal rubber sheet, something like a trampoline. When there are no masses to deform it, the sheet remains flat. But place a heavy mass, such as a bowling ball, on the sheet, and the weight of the bowling ball will deform it. Now, add a much smaller mass, a marble will do nicely, and watch as the marble falls toward the heavier bowling ball. The marble can also be given some tangential velocity so that it orbits the larger mass, much as the Earth orbits the Sun. The depression in the surface keeps the smaller mass from flying off, just as the Sun's gravity tethers the Earth. There are some misleading things about this analogy. First of all, the curvature of the rubber sheet is spatial curvature, not space-time curvature. It fails to explain the peculiar effects that masses have on nearby clocks. We will see those effects later in the chapter. Even worse, the model uses gravity to explain gravity. It's the pull of the real Earth on the bowling ball that causes the depression in the rubber surface. In any technical sense, the rubber sheet model is all wrong. Nevertheless, the analogy does capture some of the spirit of general relativity. Space-time is deformable, and heavy masses do deform it. The motion of small objects is affected by the curvature created by heavy objects. And the depressed rubber sheet looks quite a lot like the mathematical embedding diagrams that I will soon explain. Use the analogy if it helps, but keep in mind that it is only an analogy. Black holes. Take an apple and slice it through the center. The apple is three-dimensional, but the newly exposed cross-section is two-dimensional. If you stack up all the two-dimensional cross-sections obtained by thinly slicing the apple, you can reconstruct the apple. One might say that each thin slice is embedded in the higher dimensional stack of slices. Space-time is four-dimensional, but by slicing it, we can expose three-dimensional slices of space. It can be visualized as a stack of thin slices, each one representing three-dimensional space at a single instant of time. Visualizing three dimensions is a lot easier than visualizing four. The pictures of the slices are called embedding diagrams, and they help give an intuitive picture of curved geometry. Let's take the case of the geometry created by the mass of the Sun. Forget time for the moment and concentrate on visualizing curved space in the Sun's vicinity. The embedding diagram looks like a mild depression in a rubber sheet centered at the Sun, more or less similar to the trampoline with the bowling ball resting on it. The distortion near the Sun would become more pronounced if the same mass were concentrated in a smaller volume. The geometry near a white dwarf or a neutron star is even more curved, though still smooth. As we learned earlier, if the collapsing star grows small enough to be contained within its Schwarzschild radius, 2 miles for the Sun, then just like the polywogs trapped in the drain, the particles of the Sun will be irresistibly drawn in, collapsing until they form a singularity, a point of infinite curvature. What black holes are not. I'm expecting that this section will generate some irate mail from readers whose knowledge of black holes comes solely from the Disney film, The Black Hole. I don't want to be a spoilsport. Lord knows that black holes are fascinating objects. But black holes are not gateways to heaven and hell or to other universes, or even tunnels that lead back to our own universe. Since all is fair in love, war, and science fiction, I don't really mind that the movie makers took a trip to La La Land, but understanding black holes requires more than careful study of B-movies. The premise of The Black Hole actually originated with the work of Einstein and his collaborator Nathan Rosen, later popularized by John Wheeler. Einstein and Rosen speculated that the interior of a black hole might connect to a very distant place, through what Wheeler would later call a wormhole. The idea was that two black holes, perhaps billions of light years apart, could be joined at their horizons, forming a fantastic shortcut across the universe. Instead of the embedding diagram of the black hole ending at a sharp singularity, once it passed the horizon, it would open out into a large new region of space-time. Entering one end and leaving the other would be like going into a tunnel in New York and emerging after no more than a couple of miles in Beijing or even on Mars. Wheeler's wormhole was based on genuine mathematical solutions of the general theory of relativity. That's the origin of the urban myth that black holes are tunnels to other worlds. But there are two things wrong with this fantasy. The first is that Wheeler's wormhole can stay open for only a short period of time, and then it pinches off. The wormhole opens and closes so quickly that it is impossible for anything to pass through, including light. It is as though the short tunnel to Beijing would collapse before anyone could traverse it. Some physicists have speculated that quantum mechanics might somehow stabilize the wormhole, but there is no evidence for this. Even more to the point, Einstein and Rosen were studying an eternal black hole, one that exists not only into the infinite future, but also into the infinite past. But even the universe is not infinitely old. Real black holes almost certainly have their origins in the collapse of stars or other massive objects that took place long after the Big Bang. When Einstein's equations are applied to the formation of black holes, the black holes simply do not have wormholes attached to them. Now that I've spoiled your day, I suggest you rent the movie and have some fun. How to build a time machine. The future ain't what it used to be. Yogi Berra. How about time machines? Another stock science fiction gimmick and the subject of numerous books, television shows, and movies. Personally, I'd love to have one. I'm very curious about what the future will be like. Will people survive 1,000,000 years from now? Will they colonize space? Will sex survive as the preferred method of procreation? I'd love to know, and so I suspect would you. Be careful what you wish for. There would be some downsides to traveling to the future. All your friends and family would be long dead. Your clothes would look ridiculous. Your language would be useless. In short, you would be a freak. A one-way trip to the future sounds depressing, if not tragic. No problem, just climb into your time machine and set the dial back to the present. But what if your time machine's transmission had no reverse gear? What if you could only go forward? Would you do it anyway? You might think that's an idle question. Everyone knows that time machines are science fiction, but that's actually not true. One-way time machines to the future are quite possible, at least in principle. In the Woody Allen movie Sleeper, the protagonist is transported 200 years into the future by a technique that is almost feasible today. He simply has himself frozen into a state of suspended animation, something that has already been done with dogs and pigs for a few hours. When he wakes from his frozen state, he is in the future. Of course, that technique is not really a time machine. It can slow a person's metabolism, but it won't slow the motion of atoms and other physical processes. But we can do better. Remember the twins, Bob and Alice, who were separated at birth? When Alice returns from her trip into space, she finds that the rest of the world has aged far more than she has. Thus, a round trip on a very fast spaceship is an example of time travel. A large black hole would be another very handy time machine. Here's how it would work. First of all, you would need an orbiting space station and a long cable to lower yourself down to the vicinity of the horizon. You wouldn't want to get too close, and you certainly wouldn't want to fall through the horizon, so the cable must be very strong. A winch on the space station would lower you down and, after a specified time, reel you back up. Let's say you wanted to go 1,000 years into the future, and you were willing to spend 1 year suspended on the cable without too much discomfort from the gravitational acceleration. It could be done, but you would need to find a black hole with a horizon about as big as our galaxy. If you didn't mind being uncomfortable, you could do it with the much smaller black hole at the center of our galaxy. The downside would be that you would feel as if you weighed 10 billion pounds during that year near the horizon. After a year on the cable, you would be reeled in to find that a millennium had passed. In principle, at least, black holes really are time machines to the future. But what about getting back? For that, you would need a time machine to the past. Alas, going backward in time is probably impossible. Physicists sometimes speculate about time travel to the past by passing through quantum wormholes, but going back in time always leads to logical contradictions. My guess is that you would be stuck in the future and there would be nothing you could do about it. Gravitational slowing of clocks. What is it about black holes that makes them time machines? The answer is the strong distortion of space-time geometry that they produce. This distortion affects the flow of proper time along world lines in different ways, depending on where the world lines are located. Far from a black hole, its influence is very weak, and the flow of proper time is almost unaffected by its presence. But a clock suspended on a cable just above the horizon would be slowed down a great deal by the distortion of space-time. In fact, all clocks, including your own heartbeat, your metabolism, and even the internal motion of atoms, would be slowed down. You wouldn't notice this in the least. But when you returned to the space station and compared your watch with clocks that remained on board, you would notice the discrepancy. More time would have elapsed on the space station than on your watch. Indeed, it would not even be necessary to return to the space station to see the effects of the black hole on time. If you, suspended near the horizon, and I, in the space station, had telescopes, we could watch each other. I would see you and your clock in slow motion, while you would see me speeded up like an old Keystone Cops movie. This relative slowing of time near a heavy mass is called gravitational red shift, discovered by Einstein as a consequence of his general theory of relativity. It doesn't happen in Newton's theory of gravity, in which clocks all tick at exactly the same rate. The closer the clock is to the black hole horizon, the slower it seems to tick. Right at the horizon, time comes to a complete standstill for clocks that remain outside the black hole. The gravitational slowing of clocks happens in less exotic circumstances than near black hole horizons. A mild version of it happens on the surface of the sun. Atoms are miniature clocks, the electrons whizzing around the nucleus like the hands of a clock. When observed from the Earth, atoms on the sun appear to run a bit slow. the loss of simultaneity, the twin paradox, curved space-time, black holes, time machines, so many far-out, stranger-than-fiction ideas, and these are the reliable ones, the non-controversial concepts that physicists all agree on. It took some painful rewiring, differential geometry, tensor calculus, space-time metrics, differential forms, to understand the new physics of space-time. Yet even the difficult transition to the Alice in Wonderland quantum realm was nothing compared to the conceptual difficulties that baffle us now as we try to reconcile general relativity with quantum mechanics. At times in the past, it looked as if quantum mechanics could not coexist with Einstein's theory of gravity and would have to be abandoned. But perhaps one can say that the Black Hole War was the war that made the world safe for quantum mechanics. In the next chapter, I will attempt the impossibly quixotic task of rewiring you for quantum mechanics, more or less without equations. The real tools for grokking the quantum universe are abstract mathematics, infinite dimensional Hilbert spaces, projection operators, unitary matrices, and a lot of other advanced principles that take a few years to learn. But let's see how we do in just a few pages. Chapter 4. Einstein, Don't Tell God What to Do. There was a table set out under a tree in front of the house, and the March Hare and the Hatter were having tea at it. A dormouse was sitting between them, fast asleep, and the other two were using it as a cushion, resting their elbows on it and talking over its head. Very uncomfortable for the dormouse, thought Alice. Only, as it's asleep, I suppose it doesn't mind. Ever since her last science class, Alice had been deeply puzzled by something, and she hoped one of her new acquaintances might straighten out the confusion. Putting down her cup of tea, she asked in a timid voice, "Is light made of waves, or is it made of particles?" "Yes, exactly so," replied the Mad Hatter. Somewhat irritated, Alice asked in a more forceful voice, "What kind of answer is that? I will repeat my question. Is light particles, or is it waves?" "That's right," said the Mad Hatter. Welcome to the funhouse, the mad, insane, topsy-turvy world of quantum mechanics, where uncertainty rules and nothing makes sense to the sensible. Answering Alice. Sort of. Newton believed that a ray of light was a stream of tiny particles, more or less like little bullets shot from a rapid-fire machine gun. Although the theory was almost completely wrong, he invented remarkably clever explanations for many of the properties of light. By 1865, the Scottish mathematician and physicist James Clerk Maxwell had thoroughly discredited Newton's bullet theory. Maxwell argued that light consists of waves, electromagnetic waves. Maxwell's constructions were overwhelmingly confirmed and soon became the accepted theory. Maxwell pointed out that when electric charge moves, for example when electrons vibrate in a wire, the moving charge creates wave-like disturbances in much the same way that wiggling a finger in a pool of water creates waves on the surface. Light waves are composed of electric and magnetic fields, the same fields that surround electrically charged particles, electric currents in wires, and ordinary magnets. When those charges and currents vibrate, they shake off waves, which spread out through empty space with the speed of light. Indeed, if you project a light beam through two tiny slits, you can see a distinct interference pattern formed by the overlapping waves. Maxwell's theory even explained how light could come in different colors. Waves are characterized by their wavelength, the distance from one crest to the next. Imagine two waves, the first of longer wavelength than the second. Imagine the two waves moving right past your nose with the speed of light. As they pass, the waves oscillate from maximum to minimum and back again. The shorter the wavelength, the more rapid the oscillation. The number of full cycles from maximum to maximum per second is called the frequency, and it is obviously larger for the shorter wavelength. When light enters the eye, different frequencies affect the rods and cones in the retina in distinctive ways. A signal is transmitted to the brain that says red, orange, yellow, green, blue, or violet, depending on the frequency or wavelength. The red end of the spectrum consists of longer waves, lower frequency, than the blue or violet end. The wavelength of red light is about 700 nanometers. A nanometer is 1/1000th of a meter, or 10 to the -9th power meters, while the wavelength of violet light is only half that. Because light moves so fast, the frequency of oscillation is enormous. Blue light oscillates a quadrillion, 10 to the 15th power times per second. Red light oscillates about half as fast. In physics jargon, the frequency of blue light is 10 to the 15th power hertz. Can the wavelength of light be longer than 700 or shorter than 400 nanometers? Yes, but then it's not called light. The eye is insensitive to such wavelengths. Ultraviolet rays and X-rays are shorter than violet waves, and the shortest of all rays are called gamma rays. On the longer wavelength side, we have infrared rays, microwaves, and radio waves. The entire spectrum, from gamma rays to radio waves, is known as electromagnetic radiation. So, Alice, the answer to your question is that light is definitely composed of waves. But wait, not so fast. Between 1900 and 1905, a very disturbing surprise upset the foundations of physics and left the subject in a state of complete confusion for more than 20 years. Some would say it's still in confusion. Building on the work of Max Planck, Einstein completely subverted the dominant paradigm. We don't have time or space for the history of how he got there, but by 1905, Einstein was convinced that light was composed of particles that he called quanta. Later they would be known as photons. To shorten a fascinating story to its bare bones, light, when it is extremely dim, behaves like particles, arriving one at a time as if they were intermittent bullets. Go back to the experiment in which light passes through two slits, eventually arriving at a screen. Imagine dimming the light source to a bare trickle. A wave theorist would expect a very dim, wave-like pattern, just barely visible, or perhaps not visible at all. But visible or not, the expected pattern would be wave-like. That's not what Einstein predicted, and, as usual, he was right. Instead of continuous illumination, his theory predicted sudden point flashes of light. The first flash would appear randomly at some unpredictable point on the screen. Another flash would appear randomly somewhere else, then another. If the flashes were photographed and superimposed, a pattern would begin to emerge out of the random flashes, a wave-like pattern. So is light a particle, or is it a wave? The answer depends on the experiment and the question that you ask. If the experiment involves light so dim that the photons trickle through one at a time, light appears to be unpredictable, randomly arriving photons. But if there are enough photons so that they form a pattern, light behaves like waves. The great physicist Niels Bohr described this confusing situation by saying that the wave and particle theories of light are complementary. Einstein argued that photons must have energy. There was certainly evidence of this. Sunlight, photons emitted by the sun, warms the earth. Solar panels convert the sun's photons to electricity. The electricity can be used to run a motor and raise a heavy weight. If the light has energy, so too must the photons that make it up. It's clear that a single photon has only a very small amount of energy. But exactly how much? How many photons does it take to boil a cup of tea or run a 100-watt motor for an hour? The answer depends on the wavelength of the radiation. Longer wavelength photons are less energetic than shorter wavelength ones. Thus, more longer wavelength photons are needed to do a given job. A very famous formula, not as famous as E equals mc squared, but still very famous, gives the energy of a single photon in terms of its frequency. E equals hf. This formula was introduced by Max Planck in 1900. However, it was Einstein who understood that light is made of particle-like quanta, and that the formula applies to the energy of a single photon. The left side of the equation, E, represents the energy of the photon, measured in a unit called the joule. On the right side, F is the frequency, For blue light, the frequency is 10 to the 15th power hertz. That leaves h, the famous Planck's constant that Max Planck introduced in 1900. Planck's constant is a very small number, but it is one of the most important constants of nature, controlling all quantum phenomena. It ranks alongside the speed of light, c, and Newton's gravitational constant, g. H equals 6.62 times 10 to the negative 34th power. Because Planck's constant is so small, the energy of a single photon is minute. To calculate the energy of a photon of blue light, multiply Planck's constant by the frequency 10 to the 15th power hertz, and you get 6.62 times 10 to the negative 19 joules. That doesn't sound like much energy, and it's not. It would take about 10 to the 39th power photons of blue light to boil your tea. You would need about twice that number of photons of red light. By contrast with the highest energy gamma rays that have ever been detected, boiling the same cup of tea would take a mere 10 to the 18th power photons. Out of all of these formulas and numbers, I want you to remember only one thing. The shorter the wavelength of a light ray, the higher the energy of an individual photon. High energy means short wavelength. Low energy means long wavelength. Say it over a few times and write it down. Now say it again. High energy means short wavelength. Low energy means long wavelength. Predicting the future? Einstein pompously declared in a letter to Max Born, December 12, 1926, "God does not play dice." Niels Bohr's response was sharp. "Einstein," Bohr scolded, "don't tell God what to do." Both physicists were pretty close to being atheists. It would seem unlikely that either of them contemplated a deity sitting on a cloud trying to roll a 7. But both Bohr and Einstein were struggling with something totally new in physics, something that Einstein simply could not accept: the unpredictability that the strange new rules of quantum mechanics implied. Einstein's intellect rebelled at the idea of a random, uncontrollable element in the laws of nature. The idea that the arrival of a photon was truly an unpredictable event went deeply against his grain. Bohr, by contrast, may or may not have liked the idea, but he accepted it. He also understood that future physicists would have to rewire themselves for quantum mechanics, and part of that rewiring would include the unpredictability that Einstein dreaded. It wasn't that Bohr was better at visualizing quantum phenomena, or that he was more comfortable with it. Anyone who is not shocked by quantum theory has not understood it, he once declared. Many years later, Richard Feynman opined, "I think it's safe to say that no one understands quantum mechanics." He added, "The more you see how strangely nature behaves, the harder it is to make a model that explains how even the simplest phenomena actually work. So theoretical physics has given up on that." I don't think that Feynman really meant that physicists should give up on explaining quantum phenomena. After all, he was constantly explaining them. What he meant was that one can't explain quantum phenomena in terms that the human mind can visualize with the standard issue wiring. Feynman, no less than anyone else, had to resort to abstract mathematics. Obviously, reading one chapter in a book with no equations cannot rewire you, but with some patience, I think, you can grasp the main points. The first thing that physicists had to free themselves of, the thing that Einstein held so dear, was the notion that the laws of nature are deterministic. Determinism means that the future can be predicted if enough is known about the present. Newtonian mechanics, as well as everything that followed, was all about predicting the future. Pierre de Laplace, the same Laplace who imagined dark stars, firmly believed that the future could be predicted. Here is what he wrote. "We may regard the present state of the universe as the effect of its past and the cause of its future. An intellect which at a certain moment would know all forces that set nature in motion, and all positions of all items of which nature is composed. If this intellect were also vast enough to submit these data to analysis, it would embrace in a single formula the movements of the greatest bodies of the universe and those of the tiniest atom. For such an intellect, nothing would be uncertain, and the future, just like the past, would be present before its eyes. Laplace was simply laying out the implications of Newton's laws of motion. Indeed, the Newton-Laplace view of nature is the purest form of determinism. To predict the future, all you needed to know was the position and the velocity of every particle in the universe at some initial instant of time. Oh, yes, and one more thing. You would need to know the forces acting on every particle. Notice that it is not enough to know the position at an instant. Knowing the location of a particle tells you nothing about where it's going. But if you also know the velocity, both its magnitude and its direction, you can tell where it will be next. The term velocity means not only how fast an object is moving, but also the direction of motion. Thus, 60 miles per hour is not complete information about velocity. 60 miles per hour in the direction north-northwest is. Physicists speak of initial conditions, meaning everything you need to know at one instant in order to predict the future motion of a system. To understand what determinism means, let's imagine the simplest possible world. A world so simple that it has only two states of being. A coin is a good model, the two states being heads and tails. We also need to specify a law that dictates how things change from one instant to the next. Here are two possibilities for such a law. The first example is very tedious. The rule is, nothing happens. If the coin shows heads at one instant, it shows heads at the next instant, say a nanosecond later. Likewise, if it shows tails at one instant, it shows tails at the next instant. The law can be condensed to a simple pair of formulas. Heads to heads, tails to tails. The history of the world is either heads, 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 or tails, 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 endlessly repeated. If the first rule is boring, the next one is only slightly less so. Whatever the state at one instant, a nanosecond later it flips to the opposite state. Symbolically, it can be expressed this way: heads to tails, tails to heads. History would take the form heads, tails, heads, tails, heads, tails, heads, tails, or tails, heads, tails, heads, tails, heads, tails, heads. Both rules are deterministic, meaning that the future is completely determined by the starting point. In either case, if you know the initial condition, you can predict with certainty what will happen after any length of time. Deterministic laws are not the only possibility. Random laws are also possible. The simplest random law would be that whatever the initial state happens to be, at the next instant it is randomly heads or tails. A possible history, beginning with tails, would be tails, 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 heads, 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 tails, tails, heads, heads, tails, heads, heads, tails, tails. But tails, tails, heads, tails, heads, heads, tails, heads, 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 tails, tails also would be possible. In fact, any sequence would be possible. You can think of either a world without a law or a world in which the law is a random updating of the initial condition. The law needn't be purely deterministic or purely random. These are extremes. A mostly deterministic law with just a touch of randomness is possible. The law might say that with probability 9/10 the state stays unchanged, and with probability 1/10 it flips. A typical history would look like this: heads, 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 tails, 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 heads, 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 tails, 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 tails. In this case, a gambler could make a pretty good guess about the immediate future. The next state will most likely be the same as the present state. He might even be a bit bolder and guess that the next two states will be the same as the present. His chances of being right would be good, provided he didn't push it too long. If he tried to guess too far into the future, his odds of being right would not be much better than even. This unpredictability is exactly what Einstein was railing against when he said, "God doesn't play dice." You may be a bit puzzled by one point. A sequence of real coin tosses is a lot more like the totally random law than either of the deterministic laws. Randomness seems like a very common feature of the natural world. Who needs quantum mechanics to make the world unpredictable? But the reason that an ordinary coin toss is unpredictable, even in the absence of quantum mechanics, is just plain sloppiness. Keeping track of every relevant detail is usually too difficult. A coin is not really an isolated world. The details of the muscles that move the hand that flips the coin, the air currents in the room, the thermal vibrations of the molecules in both the coin and the air are all relevant to the outcome, and in most cases all this information is far too much to deal with. Remember, Laplace spoke of knowing all forces that set nature in motion, and all positions of all items of which nature is composed. Just the tiniest mistake in the position of a single molecule could ruin the ability to predict the future. But this ordinary sort of randomness was not what bothered Einstein. By God playing dice, Einstein meant that the deepest laws of nature have an unavoidable element of randomness that can never be overcome, even if every detail that can be known is known. Information never dies. One compelling reason for not allowing randomness is that in most cases it would violate the conservation of energy. See Chapter 7. This law states that although energy comes in many forms, and it can change from one form to another, the total amount never changes. The conservation of energy is one of the most accurately confirmed facts of nature, and there is not much room to tamper with it. Random kicks would change the energy of an object by suddenly speeding it up or slowing it down. There is another very subtle law of physics that may be even more fundamental than energy conservation. It's sometimes called reversibility, but let's just call it information conservation. Information conservation implies that if you know the present with perfect precision, you can predict the future for all time. But that's only half of it. It also says that if you know the present, you can be absolutely sure of the past. It goes in both directions. In the heads-tails world of a single coin, a purely deterministic law would ensure that information is perfectly conserved. For example, if the law is heads to tails, tails to heads, both the past and the future can be perfectly predicted. But even the smallest amount of randomness would ruin this perfect predictability. Let me give another example, this time with a fictitious three-sided coin. A die is a six-sided coin. Call the three sides heads, tails, and feet, or H, T, and F. Here is a perfectly deterministic law. H to T, T to F, F to H. To visualize the law, it helps to draw a diagram. In a clockwise circle, H goes to T, T goes to F, F goes to H. With this law, the history of the world, starting with H, would look like this: HTF, 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 ad infinitum. Is there a way to experimentally test information conservation? In fact, there are many ways, some feasible and some not. If you were able to control the law and change it at will, there would be a very simple way to test it. In the case of the three-sided coin, here is how it would work. Start the coin in one of its three states, and let it run for some definite length of time. Assume that every nanosecond the state flips from H to T to F, cycling among the three possibilities. At the end of the time interval, change the law. The new law is just the old law run in reverse, counterclockwise instead of clockwise. T to H, H to F, F to T. Now, run the system in reverse for exactly the same length of time that you ran it forward. The original history will undo itself, and the coin will return to the starting point. No matter how long you wait, the deterministic law will retain perfect memory and always return to the initial conditions. To check information conservation, you would not even need to know the precise law, as long as you knew how to reverse it. The experiment will always work as long as the law is deterministic, but it will fail if there is any randomness, unless the randomness is of some very subtle kind. Now let's come back to Einstein, Bohr, God, read the laws of physics, and quantum mechanics. Another of Einstein's more famous quotes is, "The Lord God is subtle, but malicious he is not." I don't know what made him think that the laws of physics are not malicious. Personally, I occasionally find the law of gravity quite malicious, especially as I get older. But Einstein was right about subtlety. The laws of quantum mechanics are very subtle, so subtle that they allow randomness to coexist with both energy conservation and information conservation. Consider a particle. Any particle will do, but a photon is a good choice. The photon is produced by a light source, a laser, for example, and is directed toward an opaque sheet of metal with a tiny hole in it. Behind the hole is a phosphorescent screen that flashes when a photon hits it. After some time, the photon may pass through the small hole, or it may miss the hole and bounce off the obstruction. If it goes through the hole, it will hit the screen, but not necessarily directly opposite the hole. Instead of going in a straight line, the photon may receive a random impulse as it passes through the hole. Thus, the final position of the flash is unpredictable. Now remove the phosphorescent screen and redo the experiment. After a short time, the photon will either hit the metal sheet and bounce off, or it will pass through the hole, having gotten a random kick. Without anything to detect the photon, it is impossible to say where the photon is and in what direction it's moving. But imagine that we intervene and reverse the law of photon motion. The experts among you may wonder whether it is really possible to intervene and reverse a law. In practice, it is usually not possible, but for certain simple systems, it is not difficult. In any case, as a thought experiment or a mathematical exercise, it is entirely doable. What should we expect if we run the photon in reverse for the same length of time? The obvious expectation is that the randomness run backward is still randomness, will ruin any hope that the photon will return to its original location. The randomness of the second half of the experiment should compound the randomness of the first half and make the photon's motion even more unpredictable. Yet the answer is much more subtle. Before I explain it, let's briefly go back to the experiment involving the three-sided coin. In that case, we also ran a law in one direction and then reversed it. There was one detail of the experiment that I left out: whether or not anyone looked at the coin just before we reversed the law. What difference would it make if someone had? It would make no difference, as long as looking at the coin doesn't flip it to a new state. That doesn't seem like a very stringent condition. I have yet to see a coin jump into the air and flip just because someone looked at it. But in the delicate world of quantum mechanics, it's not possible to look at something without disturbing it. Take the photon. When we run the photon in reverse, does it reappear at its original location, or does the randomness of quantum mechanics ruin the conservation of information? The answer is weird. It all depends on whether or not we look at the photon when we intervene. By look at the photon, I mean check where it is located, or in what direction it is moving. If we do look, the final result, after running backward, will be random, and the conservation of information will fail. But if we ignore the location of the photon, do absolutely nothing to determine its position or direction of motion, and just reverse the law, the photon will magically reappear at the original location after the prescribed period of time. In other words, quantum mechanics, despite its unpredictability, nevertheless respects the conservation of information. Whether the Lord is malicious or not, he is certainly subtle. Running the laws of physics backward is perfectly feasible, mathematically speaking. But really doing it? I very much doubt that anyone will ever be able to reverse any but the simplest systems. However, whether we can carry it out in practice or not, the mathematical reversibility of quantum mechanics, physicists call it unitarity, is critical to its consistency. Without it, quantum logic would not hold together. Then why did Hawking think that information was destroyed when quantum theory was combined with gravity? To boil the argument down to a slogan, information that falls into a black hole is lost information. To put it another way, the law can never be reversed because nothing can return from behind the horizon of a black hole. If Hawking had been right, the laws of nature would have had an increased element of randomness, and the entire foundation of physics would have collapsed. But we'll return to that later. The uncertainty principle. Laplace believed that he could predict the future if only he knew enough about the present. Unfortunately for all the would-be fortune-tellers in the world, it's not possible to know both the position and the velocity of an object at the same time. When I say that it's not possible, I don't mean that it's very hard or that present technology isn't up to the task. No technology that obeys the laws of physics can ever be up to the task. No more than improved technology can allow faster-than-light travel. Any experiment designed to simultaneously measure both the position and the velocity of a particle will come up against the Heisenberg uncertainty principle. The uncertainty principle was the great divide that separated physics into the pre-quantum classical era and the postmodern era of quantum weirdness. Classical physics consists of everything that came before quantum mechanics, including Newton's theory of motion, Maxwell's theory of light, and Einstein's theories of relativity. Classical physics is deterministic. Quantum physics is full of uncertainty. The uncertainty principle is a strange and audacious claim that was made in 1927 by the 26-year-old Werner Heisenberg shortly after he and Erwin Schrödinger discovered the mathematics of quantum mechanics. Even in an era of many unfamiliar ideas, it stood out as especially bizarre. Heisenberg made no claim that there was a limitation on how accurately one could measure the position of an object. The coordinates that locate a particle in space can be determined to any desired degree of precision. He also put no limitation on how accurately the velocity of an object could be measured. What he claimed was that no experiment, however complex or ingenious, could ever be designed to measure both position and velocity simultaneously. It is as though Einstein's God had made sure that no one could ever know enough to predict the future. The uncertainty principle is all about fuzziness, but paradoxically, there is nothing fuzzy about it. Uncertainty is a precise concept involving probability measures, integral calculus, and other fancy mathematics. But to paraphrase a well-known expression, a picture is worth 1,000 equations. Let's begin with the idea of a probability distribution. Suppose that a very large number of particles, let's say 1 trillion, are studied by measuring their positions along the horizontal axis, also called the x-axis. The first particle is found at x equals 1.3257, and the second at x equals 0.9134, and so on. We could make a long list of the location of every particle. Unfortunately, the list would fill about 10 million books as big as this one, and for most purposes we would not be terribly interested in that list. It would be much more enlightening to have a statistical graph showing the fraction of particles found at each value of x. Imagine a bell-shaped curve sweeping from just behind the vertical axis on the left up to a pinnacle above x equals 1 and back down to just past x equals 2. A glance at the graph tells us that most of the particles were found near x equals 1. For some purposes, that might be enough, but just by eyeballing the graph, we can be a good deal more precise. About 90% of the particles were between x equals 0 and x equals 2. If we had to gamble as to where a particular particle was found, the best guess would be at x equals 1, but the uncertainty, a mathematical measure of how wide the curve is, would be about 2 units. Of course, the bell-shaped curve extends beyond that estimated width, so there is some possibility of finding particles in the outlier regions. The mathematical uncertainty tells us the range of likely values. The Greek letter delta is a standard mathematical symbol for uncertainty. In this example, delta x would represent the uncertainty in the x-coordinate of the particles. Let's do another thought experiment. Instead of measuring the locations of the particles, we measure their velocities, counting them positive if a particle moves to the right, and negative if it moves to the left. This time the horizontal axis represents the velocity, v. The bell curve reaches its pinnacle on the left of the vertical axis and sweeps down just to the right of it. From the graph you can see that most of the particles move to the left, and you can also get a good idea of the uncertainty in the velocity delta v in the estimated width of the bell curve. Roughly, what the uncertainty principle says is this. Any attempt to shrink the uncertainty of the position will inevitably expand the uncertainty of the velocity. For example, we might purposefully select only those particles in a narrow range of x, say between x equals 0.9 and x equals 1.1, throwing out all the rest. For this more precisely chosen subset of particles, the uncertainty would be only 0.2, 10 times smaller than the original delta x. We might hope in this way to beat the uncertainty principle, but it doesn't work. It turns out that if we take that same subset of particles and measure their velocities, we find the velocities much more scattered than in the original sample. You may wonder why this is so, but I'm afraid it is just one of those incomprehensible quantum facts that has no classical explanation. One of those things about which Feynman said, "So theoretical physics has given up on explaining that." Though incomprehensible, it is an experimental fact that whatever we do to shrink delta x inevitably results in an increase in delta v. Likewise, anything that shrinks delta v results in an increase in delta x. The more we try to pin down the location of a particle, the more uncertain we make its velocity, and vice versa. That's the rough idea, but Heisenberg was able to make his uncertainty principle more precisely quantitative. The uncertainty principle asserts that the product of delta v, delta x, and the mass of the particle, m, is always greater than Planck's constant, h. m delta v delta x is greater than h. Let's see how it works. Suppose that we are very careful to prepare the particles so that delta x is extremely small. That forces delta v to be large enough so that the product is bigger than h. The smaller we make delta x, the larger delta v has to be. How is it that we don't notice the uncertainty principle in daily life? While driving, have you ever experienced an increased fuzziness in your location when you looked carefully at the speedometer? Or seen the speedometer go crazy when you were checking the map to see where you were? Of course not. But why not? After all, the uncertainty principle doesn't play favorites. It applies to everything, including you and your car, as well as to electrons. The answer involves the mass that appears in the formula and the smallness of Planck's constant. For an electron, the very small mass tends to cancel the smallness of h, and thus the combined uncertainties, delta v and delta x, must be fairly large. But the mass of a car is huge compared to Planck's constant. For that reason, delta v and delta x can both be unmeasurably small without violating the uncertainty principle. You can now appreciate why nature didn't prepare our brains for quantum uncertainty. There was no need. In ordinary life, we never encounter objects light enough for the uncertainty principle to matter. So, that's the Heisenberg uncertainty principle, an ultimate catch-22 guaranteeing that no one can ever know enough to predict the future. We'll revisit the uncertainty principle in Chapter 15. This book is continued on Disc 3.